Hello students, in this module we will start discussing about the CDMA mobile radio network. In the last module we have learnt about the different multiple access techniques that are opted in a mobile communication environment using space spectrum communications, and we have heard about the term code division, multiple access. CDMA network is basically exploiting that code division multiple access as a technology for the multiple access, providing the multiple access support among the different users. And we understand that all the users are simultaneously accessing the same wireless medium using the same frequency and at the same time, and they are differing from each other by the means of using the PN sequence key or the code which are separating them out from each other. The main ingredient of this CDMA is that space spectrum technique, and which uses a very high rate signature pulses to enhance the signal bandwidth. We understand, because that's a fundamental of space spectrum techniques, that you take your original data signal and you multiply it with your given key and you spread the bandwidth of the signal from the required bandwidth to excessive high bandwidth, and that's where actually the processing gain will come into picture rather later in the receiver once you display the signal. And in the CDMA systems, we understand that different users we will be using different amount of the signature pulses, and we call them as well as the codes. And in a CDMA, if you ask me about what are the different CDMA networks available already deployed worldwide, they are some famous of some of the names are IS-95 and UMTS or the CDMA 2000 and WCDMA also, and so the different methods, all these kinds of the networks we have discussed that all these different kind of the methods will have their different kind of the power control and soft handover techniques that needs to be adopted inside them to be applied to control their different interference. So, little bit about the interference by the multiple access techniques we have learned in the last module. In the consecutive modules, so we will learn how actually this interference is handled in a CDMA network via different power control mechanisms and the soft handover techniques. Because interference management or interference handling is a very critical issue in deploying a CDMA network and successfully running a network, and for successful operation of any CDMA network. So, in a CDMA network, the main objective of spreading your signal, or loosely speaking, you are wasting a part of the available bandwidth, because whenever we spread a signal, we spread the bandwidth of the transmission, and we spread the bandwidth intentionally than the minimum required bandwidth of that typical data rate to be for its signal with that typical data rate to be transmitted. So, whenever we are using the extra bandwidth, the redundant bandwidth, basically this is a wastage of the bandwidth also to some extent, if we can see, but that extra bandwidth gives the robustness against actually your multiple access interference, as well as it gives you the robustness against the jammers. So, multiple access interference or MAI, or which is a major controlling parameter of the performance of your system over a CDMA network. Please remember the term, we call it as a MAI, and we will have several techniques consecutively discussing on the controlling of this MAI later on. And see, it is a very contradictory part that you cannot design simultaneously a bandwidth efficient as well as a power efficient system simultaneously. Here basically what we are talking about is that whenever we get a bandwidth, we always talk about the bandwidth is a very useful resource, and we always try to utilize a very good or bandwidth efficient system design is the first motto as a system engineer. If you start any telecommunication system design, you will see that always we try to save the bandwidth, and that's why we go for a very efficient higher level modulation schemes to get employed, and whenever we design such communication systems. But whenever we come to CDMA networks, we never talk about the bandwidth efficiency in such a way, because we understand that there is a redundant bandwidth involved in the transmission to give you the resilience against the or robustness against the multiple access interference. So we never try to use a very higher level modulation schemes. Rather, we prefer to use the BPSK or QPSK kind of the very basic modulation schemes for the CDMA network. We also utilize modulation schemes like 18 PSK or 16 QAM. Later on, we have applied to offer a little bit high speed packet transfer, and but beyond that, actually very highly dense higher modulation schemes beyond 16 QAM that you will find on the other kind of the cellular communication systems is not found in the CDMA. Furthermore, we should mention here is that channel coding plays a very important role in communication systems, because basically the channel coding, the coding we use to provide robustness of our transmitted signal against the different deep fades that happens in the over the wireless channel. And channel coding usually means that the high power efficiency has to be paid by a lower spectral efficiency, and channel coding can be interpreted as something as an additional spreading mechanism that you do. I mean, you take each and every bit of your transmitted signal and you encode it over the multiple code bits, and then actually finally it is equivalently it can be seen that it is another spreading mechanism. And while combining this channel coding applied on the CDMA network, which in extreme case we can think something like this, that all the spreading will be done by the channel coding for each and every signal, and then the PN sequence can serve as the identity of the user to get the user separated. So channel coding combined with the spread spectrum with the spreading sequence, we can think of like this. Channel coding will be helping you to provide resilience against the deep fade from the channel, as well as he will provide you the basic spreading mechanism to spread you over a bandwidth, and he will also provide you the PN sequence can give you the user separation. But remember one thing, that the conventional spreading by this PN sequence as a repetition code combined with this repeated transmit symbols, and it can be multiplied by a pseudo random sign. So conventional spreading is nothing but this, actually a PN sequence as a repetition code and combined with the repeated transmit symbols. So the symbols that will be repeated capital N times at a clock rate, that should be understood, because that rate, the factor by means actually the clock rate is increased automatically because of spreading. It is given by the processing gain Ts by Tc, and we will be scramble that once again by some random sign, and once we do it, this is basically the time delay diversity equivalent to that we are talking about. So it is over the time that you are repeating your signals, and that's why we call it a time delay diversity. It's a time diversity that the spreading is providing you. Because of this time dispersion of the channel, we may get a multipath diversity gain that we have seen via the rec receivers, and because of this, the rec receiver structure we will see quickly in the next, that we have also earlier discussed a lot, that this time delay diversity, in order to maximize the diversity gain, the typical kind of the receiver architecture that can capture this diversity gain is the rec receiver, who consists of a series of the bank of the correlators, and the correlators are designed such that we call the correlators as the search fingers also. Correlators are designed in such a correlators are designed in such a way that their task will be to determine the propagation delays corresponding to each and every relevant propagation path, and thus this propagation techniques we expect the propagation paths, if the correlator is identifying properly, you will be getting at the output actually the peaks corresponding to the delay of this each of the signals. Let us see quickly the figure of this rec receiver, it will be understood much more easily. In the transmitter you have data symbol, you have spread it with the code C. The spread signal after the after the RF processing, they are the modulated chips basically, and they are released in the by the antenna, they are released in air in the wireless channel, and they will have different propagation path associated with it. And let us assume we are having the 4 different paths, each of the paths are having their delays from tau 1 to tau 4. And once actually you have received the signal in the RF, rec receiver architecture inside the RF is a bank of the correlators. Each of the correlators is capable of giving a match to actually they are basically the match filters independently, and they are having a correlation peak with respect to the independent path delays. So I can at the output of the correlators, all these correlators, I can have a maximal ratio combining technique running at the output. And if I see actually what's the output coming at the end of the correlators itself, you will be able to see that each of the correlator output is basically giving a correlated signal peak at that corresponding delays of their independent path. So you can identify the different multiple paths and their corresponding delay of occurrence when the signals are occurring accordingly in that corresponding to a typical path. So multiple paths can be detected according to their delay in a receiver architecture, rec receiver architecture. So now with this understanding of rec receiver and code division multiple access technique, let us now slowly enter into the network architecture, cellular mobile radio network architecture. Here we understand that the frequency spectrum assigned to a mobile radio network is separated into several frequency carriers, which themselves may further be divided into either time over the time or over the codes for CDMA, and to generate different radio channels. And since the mobile radio networks, there are many millions of the subscribers compared to the very few amount of the radio channels that we are getting. Hence, to cover a very large area, what we do is we divide the coverage area of a wireless communication over the cells, and there are multiple such cells, and each of the cells are having either the same frequency carriers or the frequency carriers within the cells can be reused also. So this is a very typical example of a cellular radio network. We will see the situation in the next slide. And this radio coverage within the each and every cell is provided by a base station, and whenever we have the different users, the way they are connected, they may be connected by the multiple access techniques, variable multiple access techniques to the base station, and each base station they may have actually multiple mobile stations associated with them within that coverage zone. Whenever some communication will go on from the mobile station to the base station, we will call it the uplink or the reverse link, and when some communication will be there from the base station towards the user side or the mobile station side, we will call them downlink or the forward link. Let us see the structure. Typical architecture of a cellular radio network is shown here in this figure number 2. Given zone, wireless communication zone is, or covering area is divided into number of the smaller cells. The cell structure is not oval, is not circular. We prefer to go ahead with a regular hexagonal shape rather. This is because if we go ahead with a circular shaped cellular architecture, and then you will have some portions left unattended at all, but it won't be covered by any of the base stations, or otherwise the cells will be overlapped with each other to have a covering zone. So overlapping cell will have lot of problems related to the interference, and actually handling the users who will be in the common areas. And so, to avoid all that, the geographic area, it is preferable to divide the geographic area by some hexagonal structure. Inside each and every hexagonal structure, one base station is taking care of the communication system. So, whenever the, as I told in the last slide, that whenever some communication will be going on between mobile station to the base station, we call it uplink, and when the communication will come from base station to the mobile station, it will be downlink. The multiple base stations, they will be connected with each other via a base station controller, or sometimes it is also called a radio network controller. And multiple base station controllers will be connected in the via the mobile station controller. And remember one thing, whenever actually you will be having a call from one cell to the next, so it means the communication is required via the base station controller to the mobile station controller to that corresponding base station. Also, whenever we will talk about the handover, I mean, suppose you are a moving user, and within the cell you are, if you are a user of this cell, you are associated with the cell this, and suppose you with your mobile you are crossing the boundary of this cell and you are entering into the another cell, then your control should be handed over, your call should be handed over from one base station to the next base station. Usually that handover is done by several ways. It may be a soft handover or it may be a hard handover. So, we will discuss about that later. This hard handover, as I was talking about, that hard handover is performed in the GSM networks. The way it is done is, whenever the mobile station reaches at the boundary of any cell, suppose this is the boundary of the cell and mobile station is crossing the boundary, he just leaves one channel and he just joins the channel which corresponds to the next cell and the base station, that such that it can be served by the next base station. So, whenever you are releasing one channel and then actually opting some other channel, in between some time is will be definitely there where you won't get any connection from any channel, because there is an interruption always associated with it. So, that is the main problem of your hard handover. In CDMA, we do not prefer to go ahead with the hard handover, we prefer to go ahead with the soft handover, where we have discussed about this earlier. The soft handover means you are having actually, or a particular mobile station is always getting screened or getting supervised by the numbers of the base stations. So, that actually whenever some cell border will come, so the smooth transition from the one base station to the next base station can be easily happen without any interruption. And because of the soft handover also there won't be actually call drop whenever you are crossing the cell boundaries. And we understand actually that whenever it needs to happen, at every moment the mobile station is served by a base station from the maximum signal level received. So, we call it that ideal power budget handover. So, how the handover will happen is based on basically every time the mobile station information in terms of the received signal power is getting updated at the base station. So, whenever it goes below some a certain level, it actually the handover it gets initiated. So, we call it the ideal power budget handover, but remember, if you are going ahead with an ideal, always follow the ideal power budget handover, which can be suddenly actually having a fluctuating figure because of the fluctuation happening inside the wireless channel. It may happen that channel has got a very deep fade for a certain period of the time, due to which your ideal power budget has gone down before a certain limit. Then if you do the handover based on the only ideal power budget, so several times back and fro kind of, or backward and forward handovers can be is possible to happen. To avoid that, no, we prefer to stay actually with multiple of a certain period, and we try to measure the level of the budgets of this received power level over a certain period of the time, and if for the continuous period, If we find actually that the power is really very low, becoming very low, then only actually we initiate the handover to avoid the back and flow handover several times. This point we have discussed. Now there is a unique concept in the CDMA network which is called the frequency reuse and the homogeneous hexagonal networks and the frequency reuse concept. This is what you know, it is a very widely used model for comparing the mobile networks, and base stations are placed on the regular, where base stations are placed over the regular hexagonal grid. Let us assume that the base stations are having omnidirectional antennas, and radio propagation loss depending only on the distance between the base station and the mobile stations are happening, and there is no other loss at this moment. And let us see the hexagonal networks that we are talking about, and what is the meaning of the frequency reuse I will explain with respect to that hexagonal structure. Remember one thing, if I am having total capital N number of the carriers to be used for this hexagonal structure, and that capital N carriers are divided into say some numbers of the disjoint sets, and then this number is called the cluster size k. Okay. And remember, whenever one cell will utilize the same frequency of the kth cluster of the, then these two cells will be called the co-channel cells. Okay. It is something like this. Let us first understand with cluster 1. Cluster 1 means we are having these hexagonal structures of the cells. Now see actually how densely that nicely and densely the whole area is covered. When I am writing the number 1 in all the cells, that means it is the same set of the frequency users. Suppose capital N is the available number of the carriers. So this capital L number of the carriers, all the carriers are utilized in each and every cell. So this is a cluster 1 kind of the architecture. Like apart from that, if I divide the capital N into suppose 3 different sets, and one of this set is used in the cluster 1, second set of the users are used, second set of the frequencies are used in cluster 2, and third set of the frequencies are used in say cluster 3. So then it will be in another cell, then actually it will be a cluster 3 configuration. In such a way, once again actually wherever the same set of the frequencies can be used in the other cells also, but the minimum distance between those two cells we call the reuse distance, and hence your one going by the same way. Suppose if I have a capital N number of the frequency channels and I have divided it into 7 number of the sets. So I will have a structure like this. Suppose this is a cell who is using the first set of the user frequency set. This is using the second set, third set, fourth set, fifth set, sixth set and the seventh set. And now see actually this is the reuse distance of using the frequency set 1. This is the distance d of using the frequency set 2. For frequency set 1, this is another user distance, reuse distance capital D. So like that way actually the network can be formed, and there are several plus points and advantages and disadvantages of using increasing the cluster size or reducing the cluster size, that we will see in the next slide. And remember one thing, the interface, before talking about the advantage and disadvantage, we should know what is the meaning of an intercell interference and what is the meaning of an intracell interference. Intercell interference is something that the interference that cell 1 is getting from the cell number 2 or cell number 7. Remember the frequencies that you are using, they may be different, and it may happen actually that the codes because of the frequency overlapping and Doppler shifts and all, some part of the interferences are expected to come from the intercells also. Intracell interference is something that within that frequency zone, within your own cell, because of the non-orthogonality of the carrier of the multiple sequences, the codes are giving you the interference. So that is the source of your co-channel sorry, it's not a co-channel, it's an intra-cell interference that you are getting because of the non-orthogonality of the codes. So intra-cell interference, that is the coming equivalent to the multiple axis interference that is coming inside the cell, and inter-cell interference is the interference that your neighbor cell is giving you. And inter-cell interference occurs in every mobile radio network with the frequency reuse, wherever the intra-cell interference can be little bit avoided if you put pure aloha, if you put the frequency division multiple access, if you put TDMA on the CDMA, like that. And that we have already seen that in a CDMA system there may be the connections share the same frequency carrier at the same time, and the intra-cell interference has to be considered because different connections cannot be separated perfectly by the code or by the time. That's unusual. And one thing we should get clearly, that if we decrease the cluster size capital K, I mean the number of the frequencies per cell, and the number of the frequencies per cell is decreasing, and hence therefore the cell capacity, the particular cell capacity is increasing. What is this? Whenever the cell size is decreasing, that means all available number of the frequencies you are utilizing for the single cell, hence its capacity increases. But remember, the mutual interference between the co-channel cells, they also keep on increasing, because you do not get the reuse distance larger, your reuse distance is reducing. So, the interference from the same cell or the co-channel cell, they are supposed to increase. So, art of the network planning will be to find out the smallest cluster size K, so that you can enhance the capacity, but you have to handle the interference level in several ways. You do the clustering in such a way that it is a reasonable amount of the signal to interference ratio you can promise with, or you can have a very nice interference cancellation scheme associated in the receiver design. And in order to handle the signal to interference ratio, we can actually opt an another technique which we call sectorization. Sectorization is like this. We have seen that if we reduce the number of the K, I mean lower cluster size is always preferable to enhance the capacity. So, let us try with the cluster 1. This is a cluster 1 omnidirectional transmission going on. Sectorization means what? Actually, within each and every cell, you can divide a cell. By another further division within the cell is possible. And if one sector is something like this, so the cluster 1 and the sector 1 is something where actually all the users are using the same number of the frequencies, but actually the sectorized antennas are getting used to focus the transmission within a typical sector. So, antennas are not omnidirectional anymore, or antennas are designed such a way, suppose if it is a 360 degree and divided by 3, so 120 degree will be the maximum transmitting zone over which, or angular zone actually, over which the transmitter will of each and every cell now will be transmitting. You can have this, which is called 1 cross 1, the whole cluster structure we will call or refer as 1 cross 1. And if we have a sector like this, that we have sectorized, and also what we have done is we have a set of frequencies. Suppose the set of frequencies is 1. We have also divided the set of the frequencies into 3 different parts, and each of this part of the frequencies are allocated to each and every sector. So, you have sectorized, you are using the sectorized antenna. On the top of that, you have also divided the frequencies over each of them. If this is the situation, then we will call it cluster 1 cross 3. Remember, your cluster 1 cross 3 is equivalently similar to the cluster K3 situation. It should be equal to the K3 situation, and hence that one will improve. The signal to interference will be degraded in such situation, because K3 gives you higher amount of the interference compared to the cluster 1, and that interference will be increased by 1 dB to 2 dB compared to the omnidirectional one. And we can conclude with the fact that it is always preferable to go ahead with a lower cluster size, and if you are lowering the cluster size to improve the signal to interference further in a CDMA network, please go ahead with the sectorized concept, and sectorization also should be done in such a way that actually satisfies the condition of your required signal to interference ratio. So, do not go ahead with a higher number of the sectors to some extent, because higher number of the sectors, on the top of that actually dividing the number of the frequencies or the channels also incur you some amount of the additive interference, because it becomes equivalent to the higher cluster configuration.